Great. I want to welcome everybody back from spring break. A couple of quick administrative announcements. Midterm 2 is 1 week from today, which means, among other things, there's no lectures, but there will be an optional review session. The exam will be in exactly the same rooms as last time, will be exactly the same structure as last time, exactly the same number of questions as last time, mostly focusing on the material that you saw in the last 4 homeworks 4 through 7, although there might be one question that recalls earlier mostly prerequisite material, but that will be meant as more as a sanity check than as it'll be something that intentionally will be easy if we do that. Okay. Several of you are waiting for regrades for midterm 1. Those will be back in your hands on Thursday. Then I'll bring everything back. I will have sent everybody email. I will have uploaded the corrected grades. I want to just do it all in one batch and get it done rather than having dribs and drabs. There will be a conflict exam on the Wednesday, one day after the regular exam, and watch the webpage tonight or tomorrow morning. There should be a registration form. Just like last time, and just like last time, I'm going to ask, why do you want why do you need a conflict? And if we need to reschedule, schedule the conflict at a different time than we did for midterm 1, it'll be because someone who actually needs a conflict exam has a scheduling conflict. But once we've got the exact time nailed down, which will likely be over the weekend, anyone who wants to take the conflict exam can, just by fill out the registration form sometime before Tuesday evening, so that we know how many people are coming and we can get a big room if we need one. Oh, right. And homework 7 is due today. In case you've forgotten, I know it's been a while since you've had homework due. I hope everybody's break was like the first half of mine and not like the second half. Hooray for spending 5 days in Barbados. Not so hooray for spending 48 consecutive hours in the Miami International Airport. Okay. So for the last several lectures, we've been talking about this class of problems that are typified by something called maximum flow and its dual, minimum cut. And at the last lecture, the Thursday before break, I had something that a picture that I drew up. That was, on the one hand, I had a box that talks about the shortest path problem. And over here, I had the maximum flow problem. And then both of these turned out to be special cases of something called the minimum cost flow problem. And this, in turn, is a special case of something called linear programming. Now, this is what I'm going to talk about today and on Thursday in the lectures building up to the exam. Now, the stuff that I'm talking about today and on Thursday is not going to show up on midterm 2. There will be a homework 8 that comes out early next week that will have some questions about linear programming and a question about that you need to solve by doing minimum cost flow. And these things will eventually show up on the final exam, but for the short term, this is meant, as a sort of warm up to something that we're going to see later. And mostly what the reason I'm introducing this to you is you might notice as time has gone on, I've gotten vaguer and vaguer and vaguer about the actual implementation details of the algorithms that we've been doing, which is a somewhat brave choice for an algorithms class. The reason why I've been doing this is that as we get further and further down this graph, the more difficult it is to describe things in full detail in the form that both can be implemented quickly and when you implement it, it actually runs quickly in practice. But on the other hand, there are standard software packages that people have devoted decades of their lives to make solving linear programming problems in particular very fast in practice. And it's often useful if you can phrase a problem in terms of linear programming to use what we know about linear programming to explore the parameters of the problem. And what sometimes happens is by phrasing something as a linear programming problem, and in particular by looking at the behavior of a particular algorithm called simplex running on the instance of linear programming that you get from the problem you actually care about. You can often say, oh, I can speed that up because every solution it considers has the following structure, and instead of doing arbitrary things that the simplex algorithm would do, I can replace that by doing something simple like pushing flow across a path in a graph, or by checking a single edge to see whether I need to pivot it into the shortest path tree or not. And so there's a somewhat anachronistic way of talking about how algorithms developed, where you can imagine linear programming developing first in its full generality, and people developing the simplex algorithm, and then walking backwards and say, oh, what happens if I think about the kind of linear programming problems I get when I look at maximum flow? Can I interpret the behavior of the simplex algorithm in terms of the original language of maximum flow? And if you do that the right way, you actually end up with Ford-Fulkerson. And similarly, I could say, well, take my instance of the shortest path problem and phrase it as a linear programming problem. Look at the behavior of this standard algorithm on that particular instance and try to interpret that behavior back in terms of the original graph. If you do that the right way, what you end up with is Bellman-Ford. If you do that a slightly different right way, what you end up with is Dijkstra's algorithm. Okay? So the algorithms that we've seen for shortest paths and for maximum flow really are shadows of this much more general algorithm called simplex, which I haven't told you what it is, working on this much more general set of problems called linear programming. And then again, I haven't told you what those are. Okay? And so it's not so much that I want to, I'm going to explain the simplex algorithm on Thursday. And it's not because I expect you to ever have to implement it. It's because it gives you a way of thinking about how you might actually efficiently solve problems that can be formulated as linear programming problems, either by extracting something about the behavior of this algorithm, or by saying, well, my boss bought Cplex, so I'm just going to call it. Okay. All right, so what is a linear programming problem? So this is the definition of linear programming is relatively abstract. I have some vector which I'm trying to optimize. So this vector is a sequence of d real numbers, where d represents the dimension of the space that I'm working over. Each of those real numbers represents something of interest. How much flow do I push through this edge? How much does it cost to flip this thing over here? What is the price of strawberry jam? How many soldiers do I need to send from Berlin to Prague? How many right turns do I need to make as I'm doing my rounds as a UPS driver? They just represent some number that we're interested in this vector of numbers describing some other structure that we want to optimize. And the objective is that we want to maximize the weighted sum of the d variables. So the x's here are the variables. This is a single variable. The cj's, these are constants. These are part of the formulation of the problem. So I want to find a vector x that makes this linear function as large as possible. Now, of course, with nothing else, if this were the only thing, there's no solution, because what I could do is find the constants c that are positive and plug in positive infinity for the corresponding x's, and find the constants that are negative and plug in negative infinity for the corresponding x's, and then the maximum value you get here is infinity. In other words, you can make it as large as you want. But then there's going to be some additional constraints that I want to impose on this. And these additional constraints are going to take the form of linear inequalities. Let's do it this way. Aij times xj is at most bi for I equals 1 to p. And again, the aij's and the bi's are all constants. These are part of the formulation of the problem, right? So I've got some inequalities that are upper bounds, I've got some inequalities that are lower bounds, and I've got some inequalities that are actually just equals, okay? But the left-hand side of all of these is just some linear combination of the xj's. Here, I say for I goes from p to, p plus 1 to q, and then this is for I goes from q plus 1 up to n. Okay? So I want to optimize some linear function of this unknown vector subject to linear constraints on this unknown vector. Okay? Now, I find, the first time I saw this, it was like, bleh, symbols. So I want to draw a picture of what this actually looks like in the case when d is equal to 2. Okay, when d is equal to 2, the vector that I'm trying to optimize is the vector x1, x2. I'll simplify that and just call the two variables x and y. Okay. So I want to find a point in the plane, represented by these coordinates x and y, that maximizes some linear function. So what that means is that I want to find a point in the plane that is furthest in some direction, subject to the later constraints. This vector that I've drawn here in terms of the direction, this is the vector c1, c2. And you might notice that's just a dot product up there. And then I want to optimize this subject to some constraints. And the constraints are going to be of the form ax plus a prime y is at most b. or ax plus a prime y is at least b. And what this means in terms of the plane is that there's some line, and I require the point to be on a particular side of that line. Okay. Sometimes it's above, sometimes it's below. Okay. So each of these constraints, if they're less than or equal to constraints or greater than or equal to constraints, I'm specifying a line, and I'm telling you that I only care about points that are above that line, or I only care about points that are below that line, depending on whether I do greater than or equal to or less than or equal to. If I had an equals constraint, that would mean I only care about points that are on this line. But for the example, let me not put any constraints like that, because it just makes the picture a little bit more confusing. Okay? And then what if I look at the set of all points that satisfy these linear constraints, I get this convex region in the plane. It's convex polygon, in fact. And what I'm looking for is, out of all points inside this convex polygon, which one is furthest in that particular direction. So in this particular case, it's a little bit difficult to tell, but I think actually this point's going to win. Okay. Now, the nice thing about doing everything in terms of geometry is that I can apply simple transformations to the geometry that don't change the fundamentals of the problem, which are a little bit more difficult to see in this sort of symbolic form at the top of the screen. So, in particular, I can just rotate the entire problem when I was wrong. That is, in fact, not the best point. Maybe, nope. This is the lowest point. So up to a possible change of coordinates, the linear programming problem is, here is a convex region defined by intersecting a bunch of linear half spaces. In the plane, the half planes on one side or the other of a line. And the objective function is find the lowest point in that region. Okay? And you know, if I phrase it in terms of arbitrary objective functions, I mean, that means rotating this picture. But fine, I'll just change the coordinate system so that essentially this vector of C1 through CD is 0, 0, 0, 0, 0, 0, 0, minus 1. Which means furthest down that I can go. Okay. I'm going to refer back to this geometric picture over and over again when I talk about the simplex algorithm in particular. But I want you to imagine that whenever we're talking about linear programming, if you get lost in the symbolism, think back at this picture. This is the problem that we're solving. Got some convex region, and I want to find the lowest point in that region. Now, it's really hard to visualize things in higher than 2 dimensions, but a lot of the intuition that you might get from this picture still carries over into higher dimensions. So, in particular, if we're working in 3 dimensions, then the constraints are not going to define a convex polygon, but rather they're going to define some sort of convex polyhedron. But it is still the case that up to a change of coordinates, I want to find the lowest point inside that convex polyhedron. And the way this convex polyhedron is specified in terms of the formal input is for every facet of this polyhedron, I specify the equation of that's satisfied by all points on that facet, which is again just going to be a linear equation. And then by setting the inequality one way or the other, I'm going to specify, oh, I want everything above that hyperplane or everything below that hyperplane on one side of the hyperplane or the other. This convex region is just the intersection of all those linear half spaces, intersecting, in this case, in free space. Okay. So that's what it is in sort of full generality. It's a little bit easier also to talk about these things if I adopt a somewhat more abbreviated notation by taking advantage of the fact that these are really vectors. The feature thing that I'm trying, this point that I'm trying to optimize, in this case that's a 3-dimensional vector, over here that's a 2-dimensional vector. The objective function is specified by a vector C. The inequalities are being specified by a matrix A with the entries Aij, and the right-hand sides of the inequalities are specified by another vector B. Okay, so it's somewhat easier if I adopt what's called canonical form, which of course I can't spell. It's a kind of mechanical exercise to take the general form of a linear programming problem and transform it into this canonical form. So in a maximize C dot X, that's a dot product. It's the sum of the corresponding pairwise products. Subject to the constraint, which I'm going to write as AX is less than or equal to B, and an additional constraint, X is greater than or equal to 0. So what this means, for example, is x1 is greater than or equal to 0, x2 is greater than or equal to 0, up through xd is greater than or equal to 0. What this phrase means is really this. Okay, so if I look at every row of the matrix A, a row of a matrix is really a vector. I take the dot product of that vector with the vector x, and I want it to be less than or equal to the corresponding entry in the vector b. I'm just summing up, I'm taking that collection, in fact, that whole collection of inequalities, and I'm just going to write it in the simple form ax is less than b, or less than or equal to b. All right, so this means sum over all I, aij xj is at most, I, that should be sum over all j. Okay. So the input to, in terms of linear algebra, the input to a linear programming problem is a matrix A, a vector B, and a vector C. And I interpret the matrix A and the vector B as a series of linear constraints, which again define this convex region in whatever dimensional space I'm in. And I want, and I also have these non-negativity constraints, which are there for somewhat technical reasons. And I want, among all points x that satisfy these constraints, I want the one that maximizes the dot product with this objective vector C. Okay. Okay. So this is the generality. I want to give a couple of examples because I know the first 8 times I saw this, it didn't go in until I actually walked through several examples. But before we get to that, are there questions that occur to people now about how to formulate this problem? What this means? Okay. So maybe what I should do is start with an example that is hopefully familiar by now, because we've been talking about it for several weeks. namely the maximum flow problem. Okay? So, recall that for the maximum flow problem, what are you given as input? You're given a graph with vertices and edges. It's a directed graph. For every edge, you're given a capacity, which represents the maximum amount of flow that you can push through that edge. And you want to maximize the total net flow out of a specific vertex called S, subject to some constraints. And some of those constraints are the flow through this edge has to be non-negative, the flow through this edge has to be less than the capacity, the flow into this vertex must be the same as the flow out of this vertex. If I think of the various flow values as coefficients of a vector, so I have one flow value for every edge, so I have an e-dimensional vector of real numbers, then the constraints that the maximum flow problem imposes are linear constraints. The objective that I'm trying to optimize is a linear function. So I can write this specifically as follows. Okay, I want to maximize the total flow out of S. So I'm gonna let F represent the flow. I'm going to write it with subscript notation because it's a little bit easier sometimes to think of vectors as vectors when they're written in vector notation instead of with functional notation, the way we've done it before. Okay, so this is a linear function of the various flow values. Namely, I have a coefficient of +1 on every edge leaving S, and I have a coefficient of -1 on every edge coming into S, and I have a coefficient of 0 on every edge that doesn't touch S at all. Now I have some constraints. The biggest constraint is that I have flow conservation. Like I say, for every vertex that isn't S or T, I have, again, this linear combination of flow values, which is constrained to be equal to 0. Right? Remember, this is one of the three ways that we can have linear constraints. We can either have upper bounds, or we can have lower bounds, or we can have equality constraints. The second thing is that every flow value must be at most the capacity of that edge, and every flow value must be positive or non-negative. Okay, so the F's are the vector that I'm trying to optimize. The matrix A, in this case, all the coefficients on the left-hand sides of these constraints they're all 0s or 1s or -1s. Right, so I have a bunch of 1s and -1s here. For the rows, for the capacity rows, I have a 1 on this edge and a 0 on every other edge. And similarly here, I have a 1 and a bunch of 0s. Okay. The right-hand side of these constraints, the vector that we were calling B in the more general form, I have a bunch of 0s, 1 for each vertex that isn't S and T. I have a capacity value, which is given to me as part of the input for every edge, and I have a bunch more 0s. The objective vector, which is again sort of given to me as part of the formulation of the problem, is again a bunch of 0s, 1s, and -1s, where a 1 or a -1 indicates that the corresponding edge touches S, and the sign tells you whether I'm touching under the head or the tail. And so this is a linear programming problem. Okay, so that's example number 1. Does everybody see that this is in fact a linear programming problem? Don't worry for the moment about what that means, other than satisfying the definitions. Okay, so there was another problem related to maximum flows called minimum cuts. And I want to imagine that maybe I can also think of this as a linear programming problem. Now, at some level, we already know that we can think of this as a linear programming problem because we know that we can solve minimum cuts by just computing a maximum flow and then doing some post-processing, looking at all the vertices that you can reach from S in the residual graph. But I want to actually do a direct formulation of the minimum cut problem as a linear program. And so this requires me to think of what the variables might be that I'm actually trying to optimize. Okay. So I'm going to define a variable called x for every vertex that intuitively this means u is on the source side of the cut and v is on the target side of the cut if it's equal to 1 and it's equal to 0 otherwise. Now, I'm not saying this as a definition. I'm writing this down as intuition, which means that I have to put a fuzzy cloud around it and say, okay, this is what I'm thinking if I stand here. And now, if I imagine that I have variables that mean these things, can I set up some sort of objective function that I would like to minimize or maximize? Can I set up some constraints that these variables have to satisfy in order to enforce what I think minimum cuts actually behave like? So the first thing is, well, this edge, this is an indicator variable that indicates that an edge is crossing the cut in a way that contributes to the cost of the cut. So if I want to minimize the total cost of the cut, what I want to minimize is some weighted sum of these x's, where the weight that I assign is the capacity of the corresponding edge. So I want to minimize the sum over all edges from u to v of the capacity of the edge from u to v times this variable x from u to v. If x is 1, that capacity, the corresponding capacity, is going to contribute to this objective function, making the cut more expensive. If x is 0, it's not. Okay? Now, as it stands, this is still just intuition, remember. As it stands, I don't really have enough here. Because, for example, nothing prevents me at this point from setting all these x's to 0. In fact, nothing prevents me from setting all these x's to minus infinity. Okay, so I need to establish some other constraints that sort of enforce this. So one of the things I need is I really want these variables to sit between 0 and 1. Now, I would love to be able to just say xuv is equal to 1 or it's equal to 0. Unfortunately, that is not a linear constraint. Right? Using the word or in there takes you out of the realm of specifying linear constraints. The linear constraints that you set up is it satisfies this inequality, and it satisfies this inequality, and it satisfies that inequality. It's all and. There's no way to put it in or. Okay. Later, when we talk about integer programming, I'll tell you, something else that you can do there. And I need to satisfy again these constraints for every edge uv. Okay, so this will at least prevent me from just setting all these variables to negative infinity, but it still doesn't prevent me from setting them all to 0, and that's not really what I mean. I want some way of enforcing the semantics that a 1 really means I'm crossing from the S side of the cut to the T side of the cut. So, I don't know, why don't I think of yet another variable here. S sub v, this is 1 if v is on the S side of the cut, and 0 if v is on the T side of the cut. And again, this is just intuition. I'm just essentially, brainstorming here. Maybe we can set something up that some way of associating these two variables that will at least, assuming we've got the S's right, will make the X's right as well. And it turns out the right way to say that is this. So what this says is, if I'm going to draw a couple of examples here in red. There are only going to be 4 cases that I want to consider. Okay, if both U and V are on the T side of the cut, that means both of these are equal to both of these variables on the vertices are equal to 0. Then I really want the variable attached to the edge also to be equal to 0. And so what this inequality says in that case is x of uv plus 0 minus 0 is at least 0. Okay, so at least it can be either 0 or 1, but because I'm trying to make the sum small, that's going to naturally drive it down to 0. Okay. So this is at least 0. If I have the tail in T and the head in S, this is going to translate into x from U to V plus 1 minus 0 is non-negative, which is the same as saying the variable that I want to put here is at least negative 1. Well, I already have a constraint that says it has to be at least 0, so this constraint that it has to be at least negative 1 is just redundant. And so the natural thing is to try to push the value down to 0. If both sides are in S, again, just doing the math, I'm going to say that edge has to have a variable at least 0. But if the tail is in T and the head is in S, then this is the same as this constraint is going to force the value attached to that variable to be at least 1, and therefore at most 1. Question in the back.
The second one is 1.
Sorry?
Your second one, like the first one.
Oh, I'm sorry. The last.
Sorry, yeah, that's fine.
The last one should be from 1 to 0. Thank you. Sorry. Okay. So this constraint has the effect of saying, I really don't care what you do with the edge variables when the edge doesn't cross the cut in the right way. But when the edge does cross the cut in the right way, I want that edge variable to be at least 1. Okay. All right. Now, this still doesn't keep me from setting, say, all of the S variables to 0 and all of the X variables to 0. So I need to add a couple more things to drive the whole thing home. Namely, the source node must be on the S side of the cut, and the target node must be on the target side of the cut. Now, if you walk through this actually a little bit more carefully, these constraints actually collectively constrain every variable S to lie between 0 and 1. This is not at all obvious from the way that I formulated it, but if it makes you feel better, you could put in explicit constraints that every other vertex variable has to be between 0 and 1, just the way I did with the edge variables. And, well, then we're done. This is a linear programming formulation of the minimum cut problem. Now, you should, at this point, be suspicious. There's something that I haven't told you. There's a real constraint here that I haven't told you how to enforce. That's actually not the problem, because I can always just maximize the negation. Okay, fine. I can always turn the picture upside down to make the arrow go up instead of down. That's just a coordinate change. The real problem here is, I mean, these constraints actually force all of the x variables to be between 0 and 1, and they force all of the vertex variables to be between 0 and 1. And provided that the s's and the x's are in fact integers, then this middle constraint really does enforce the right semantics. The problem is that if, how do I force the x's and the s's to be integers? Okay. For now, I'm going to ask you to believe me when I say, remember Ford-Fulkerson. Remember how the original maximum flow problem, if all of the constraints are integers, if the capacities of every edge are integers, then you can guarantee there is an integer maximum flow. Okay. That's actually an example of a much more general structure that allows you to look at a linear programming problem and tell whether some of the variables are in an optimal solution going to be integers. And it turns out that this linear programming problem satisfies that constraint. It's called total unimodularity. And someone who is well versed in linear algebra can look at the matrix that this system of inequalities defines and say, yes, in fact, the determinant of every square submatrix is either 0, 1, or -1, and therefore, there is an optimal solution where every variable is an integer. Okay? All you need to do is check total unimodularity. Okay? The other reason why I know that this linear programming problem formulation is going to work, even though it does not explicitly enforce the constraint that these x variables and s variables are integers, is that this linear programming problem is, in a formal sense, the dual of that linear programming problem. And this is not just in the sense that minimum cuts and maximum flows are sort of intuitively dual in that they come together as a pair, and if you solve one, then you solve the other. We only really know how to solve them both at the same time. But what I really mean is, for any linear programming problem, there is an evil Spock with a beard version of that linear programming problem called the dual. And typically, when the primal problem is a maximization problem, the dual problem is a minimization problem. And the way that you exchange things, I'm going to go through this in more detail, but I want to point out where the duality shows up. One thing to notice is, in the original maximum flow problem, the capacities show up on the right-hand side of the inequalities. In the minimum cut problem, the capacities show up in the objective function. But this actually goes both ways. Remember, in the original problem, in the objective function, I just had a bunch of 1s and -1s and 0s. Well, it turns out that those 1s and 0s are showing up again in the formal sense over here in the on the right-hand side of the inequalities. And if I wrote this linear programming problem out in canonical form, I'd get some matrix A that generates all of the linear constraints. And this matrix has a row for every vertex and a row for every edge, and it has a column for every edge. Over here, this, it actually turns out if I did this right, these constraints are redundant, in which case I kind of, the non-negativity constraints don't count. The only thing that I really have is a row for every edge. But then I have a column for every edge and a column for every vertex. So the constraint matrix that I get for the minimum cut problem is just the transpose of the matrix that I get for the original maximum flow problem. Okay, I'm blowing through this really fast, and I'm doing that on purpose because I don't want you to pay attention to the specific details. I want to give you the vague impression that there's more than just these are kind of related problems connection between maximum flows and minimum cuts. But rather there's actually a syntactic way of transforming the maximum flow linear program into the minimum cut linear program. Which I'm going to show you now. Okay, so here's the canonical form for a linear programming problem. Let me put this down here. Now I'm going to modify this by creating another linear programming problem. And I'm really just going to do this purely mechanically by exchanging the roles of the objective vector and the right-hand side of the inequalities, and some of the senses of the inequalities. Okay, so for every linear program in canonical form over on the right, there is another linear program which, as I've written it, is not in canonical form. Over here on the, this is, on the right, then I get this other linear program on the left. Now, just to convince you that, in fact, I can write this in canonical form, I'll go ahead and do that now. This is the maximum of B transpose dot Y transpose subject to the constraint, minus, subject to constraints that the negative A transpose times Y transpose is the most C transpose, and every element of Y transpose is positive. Okay. This is actually in canonical form. I just got rid of all the transposes and minus signs by flipping the order in which I multiply the vector by the matrix, flipping that sign inequality, and changing the max into a min. Now, what do these two linear programming problems have to do with each other? This is the fundamental theorem of LP. Fundamental theorem of linear programming. Okay, if X star is the optimum solution for the original dynamic programming problem, and Y star is the optimum solution for the dual problem, which I'll write as this upside down pi. Then the objective values are the same. All right, so the two objective values are exactly the same, and moreover, I can write this as the objective value is taking the two vectors and multiplying one on one side of the constraint matrix and one on the other. In fact, this is not even an if-then. Right? This, I should properly say, to make this the stronger version, if and only if. So in terms of maximum flows and minimum cuts, what does this mean? It's saying F is a maximum flow and ST is a minimum cut if and only if the value of the maximum flow is equal to the cost of that minimum cut. And then this expression here in the middle that expresses the objective value in terms of, well, the x's tell you the values on each edge that represent the flow values, and the y's here represent 1 if the edge crosses the cut and 0 if it doesn't, and this A represents some other constraint matrix. It's not clear that I know what the natural interpretation of this middle expression is, but it's actually very useful in sort of establishing the proof of this fundamental theorem. It's about thinking in terms of this common value here in the middle. Okay. So if I want to solve one linear programming problem, if I can transform it into its dual and solve that, that's good enough. So, in particular, if I start with maximum flows and I dualize, I'm going to get minimum cuts. If I start with minimum cuts and I dualize, I'm going to get maximum flows. Yeah. Subject to, yes. Such that. Either way. Okay. So like the maximum flow minimum cut theorem, there's an easy part of this theorem to prove, and there's a hard part of the theorem to prove. The easy part of the theorem to prove involves doing some definition chasing. This is the part where we said the value of any flow is greater than or equal to the value of any cut. And we just wrote down what it means to be the value of a flow, and we added some zeros and subtracted some zeros and applied some definitions, and we ended up with an expression that meant the cost of the cut. And there's a similar weak version of this theorem that says if x is feasible for the original problem, which means x satisfies all those constraints, although it might not be optimal. Because feasible means ax is less than b and x is greater than or equal to 0. But it may or may not maximize the objective value. It just lies in that convex yellow region that I had on the screen earlier. And y is feasible for the dual problem, then cx is at most, yax is at most, yb. Right, so this is the weak fundamental theorem of linear programming. And the proof is, well, x is feasible for pi, so that means that ax is at most b. That's just the definition for feasibility. Because y is feasible for the other one, then we know that y is non-negative. And so that means that we can actually multiply both sides of this matrix inequality by this vector y and still get a corresponding matrix inequality. Right, so this is going to imply, well, I multiply y on one side and I multiply y on the other side. And because y was non-negative, I get the second half of the theorem. And now I do the same thing in the other direction. Y is at most c, x is at least 0, and then I get the first half. Okay, so it's just definition chasing, right? The fact that flow is always greater than or equal to cut, this is just a consequence of this weak version of the theorem. It really just follows by definition chasing in linear algebra. Okay. The strong version of the theorem, on the other hand, remember for flows and cuts, we actually had to develop an algorithm to compute maximum flows. And we had to say, well, if I have a flow, if I don't have a maximum flow, then I can push more flow through. So conversely, if I can't push any more flow through, I have a maximum flow. But if I can't push any more flow through, then I have a minimum cut as well. Okay. And similarly, if I want to prove the strong version of this fundamental theorem, I really need to develop an algorithm to solve linear programming problems. That say, if x is feasible, but it's not optimal, then I need some way of making x better. And if y is feasible but not optimal, then I need some way of making y better. And ultimately, this is what the simplex algorithm is. The simplex algorithm is kind of like Ford-Fulkerson in that you start with picking something feasible and then iteratively making it better but keeping it feasible. Okay. I'm not going to walk through the formal proof of this, the strong version of the theorem, because I don't really think there's enough time, and this is already a bit of a fire hose. If you're interested, it's written up in complete detail in the notes, or in near complete detail in the notes. What I want to do instead is I want to at least give you some form of intuition about what this duality thing means, in more generality than flows versus cuts. Okay, so hopefully you kind of get the idea for flows and cuts that a flow, you're trying to move stuff from one side of the graph to the other, and a cut is a kind of bottleneck that you put on the flow. And informally, at least, the equivalence is that the smallest possible bottleneck actually is equal to the maximum amount of flow that I can push through. Okay. And there really is a sort of similar thing that gives you this equivalence, this more general duality relationship, which seems to help many people sort of become comfortable with the idea. At some level, this is something that you just memorize, and once you get your LP into canonical form, boom, there's its dual, and you go on from there. But if you want some justification for what's going on, let me try to give you some idea of where that's coming from. Okay, and so I'm going to do that by considering a specific linear programming problem. Yes? There is a dual for shortest path. So the shortest path problem is itself an example of linear programming. You can find, in fact, the the primal and dual LPs for linear programming are actually right here in the notes. The right way to think about this is, in one LP formulation of shortest paths, the variables that you're trying to optimize are the distance values you attach to the vertices. The constraints actually put upper bounds on those distances, and so somewhat counterintuitively, you're trying to maximize the distances subject to those constraints. And what the constraints look like is you have a constraint that says, so this is u and this is v. The distance value that I store at v has to be at most the distance value that I store at u plus the length of this edge from u to v. Right? So this is an upper bound on distance of v. It tries to keep it low. So in order to be feasible, these distance values have to be small. And now, subject to those constraints, I want to make the distances as big as I can. Okay, so it's a maximization problem with the variables or distances associated with the vertices, and the constraints are these inequalities associated with the edges. The dual formulation of this is actually the minimum cost flow formulation, where you imagine growing a tree out of the source, and I'm actually sending flow through the edges of the shortest path tree out to the other nodes. In this case, I have a variable for every edge instead of a constraint for every edge. And I have a constraint at every vertex that talks about flow conservation instead of having a variable for every vertex. And now I'm trying to maximize the cost going out instead of, I'm trying to minimize the cost going out instead of trying to maximize the sum of these distances. So it's not really, in this case, a different problem. It's just, well, I can look at shortest paths as computing these distances, or I can look at shortest paths as computing this flow. But if you look at the way the algorithms behave, one family of algorithms is trying to build up the flow, the other family of algorithms is trying to decrease the distances. So there's a min and a max duality between those formulations. Yeah?
So you said if we have a linear programming problem and then we can transfer it to a dual and then we solve either one, right? So
Yes.
So you mean, so it's possible that one is easier to solve than the other one? Or dual?
Oh, yes, that's absolutely the case. So the question was, once I have a linear programming problem, if I don't know how to solve the original problem, can I transform it into the dual and get something that's easier to solve? And the answer is absolutely yes. Now, in terms of computational complexity, no, because the algorithm run on the dual you can interpret as an algorithm running on the primal. But in terms of designing the algorithm and gaining intuition, then one formulation as an LP may not give you any intuition. But if you transform it into the dual, that dual formulation may provide you with some intuition that would let you design a more efficient algorithm. And more generally, being able to bounce back and forth between these two formulations, it's sort of as a general rule, the more different ways you have to think about any given problem, the more likely you are to stumble upon an efficient solution for that problem.
But you said the algorithm can interpret it that way.
Yes. And when I talk about the simplex algorithm, I'll show you how to run the simplex algorithm on the primal problem, and then I'll show you how to run the simplex algorithm on the dual problem, but in terms of the primal problem. And it'll all be pictures. There won't be, I mean, literally, it'll all be pictures. Okay. Which, if those of you who've seen linear programming before, may be wondering where all the tableaus are and where all the pivots are and why I don't have huge tables of numbers. I don't have huge tables of numbers because huge tables of numbers provide exactly zero intuition. So especially on Thursday, I'm going to try to provide just pictures that sort of explain how these algorithms work. Okay. So thank you for the shortest path question. All right, so let me put up a specific linear programming problem. Relatively few variables, relatively few constraints. So in fact, this is just going to have 3 variables and 2 non-trivial constraints. One involving just 2 of the variables and the other one involving 3. And then all these variables need to be non-negative. Let me give it a few seconds. Okay, so hopefully you can see that this problem is, this linear programming formulation is in canonical form. I have a maximization function at the top. I have less than or equal to constraints that involve various coefficients, and then I have non-negativity constraints on each of the variables. Okay. So I want to somehow transform this problem, somehow derive what its dual is. Okay, so let sigma star be the optimum value for this problem. Right? I can plug in various values of x1, x2, and x3 and check to see whether they're feasible and check to see what their objective value is. And this will give me a lower bound on this optimum value sigma star that I'm trying to compute. And so, for example, if I set x to be equal to 1, 0, 0, it's easy to see that this vector actually satisfies the various inequalities. 1 plus 4 times 0 is at most 2. 3 minus 0 plus 0 is at most 4. All these things are non-negative. This gives me an objective value of 4, so I know that sigma star is at least 4. Right, I found a feasible point. I compute its objective value. I get something, but it may not be as big as it could possibly be. Okay? Or I could plug in a different value here. So if I plug in 0, 0, 3, again, you can check just by inspection that this is going to be feasible. And this is going to give me a slightly larger value for my objective, but one that I still don't know is as large as possible. And so think about this as maximum flow. I found a flow, it was feasible, it had value 4. And then I found a bigger flow, it was feasible, it had value 9. How do I know that I can't push more flow through? And so what I really need to do is I want to derive an upper bound, somehow. Some kind of upper bound for this the optimal value here. I can keep finding points and pushing the value up, but I need to find a way to put a ceiling on it. Okay? And so to do this, I'm honestly just going to sort of flail around for a while, throw in some extra variables, and hope that something useful comes out. Which is not not necessarily a great way to build up intuition, but we'll try. Okay. So let me just pick a couple of new variables, y1 and y2. I'm going to define these new variables and say that they're non-negative. And what I'm going to do is I'm going to figure out what these variables are later. But for now, let me just think about these as maybe tools that I can use to derive an upper bound. Because they're non-negative, no matter what they are, I can modify my linear programming problem by multiplying everything on the left side and everything on the right side of these inequalities by the same y. Okay, so I'm going to multiply both sides of the first inequality by y1, both sides of the second inequality by y2. All I've done, in a sense, is a change of coordinates. I haven't changed the underlying geometry of the problem, but this gives me a little bit more slack that maybe I can play around with that will let me choose useful values for y1 and y2. And then now the next thing I'm going to do is I'm going to say, well, if I have a variable, a vector x that satisfies both of these inequalities, then in particular I must also be the case that if I sum up the left-hand sides, I get something that's smaller than if I sum up the right-hand sides. So I can write that as x2 plus y2 times 3x1 minus x2 plus x3 is at most 2y1 plus 4y2. Okay? I could throw this in as an additional constraint and nothing would change. Okay? Any feasible variable x1, x2, x3 must satisfy this particular constraint. Okay? No matter what the y's are. On the other hand, let me just suppose, for the sake of argument, well, actually, it might be useful if I wrote this out instead of as the y's multiplying expressions involving x. If I wrote this out as the x's multiplied by expressions involving y. So if I do that carefully, I've got this written down in advance, so I'm not making this up because, as we've learned many times over the semester, when I make things up, they don't go well. Okay, so I've just gathered the terms involving x1, involving x2, involving x3. Now, what I'd like to be able to do is I'd like to use this expression as an upper bound on the objective function. Right? I want to use this as an upper bound on sigma star. So if I want this to be bigger than 4 times x1 plus x2 plus 3x3, this is what I want, then what I should do is I should satisfy these constraints on sort of individual coefficients should match up in the right order. Okay, so what I would need then is y1 plus 3y2 to be bigger than 4, 4y1 minus y2 to be bigger than or equal to 1, and y2 to be bigger than or equal to 3. Oh, and let me copy down the constraints that I started with. I needed to have y1 and y2 be non-negative in order to do the multiplication thing at the beginning. Okay? Now, if I could do this, if I could find values of y that satisfy these constraints, then this expression, 2y1 plus 4y2, is greater than or equal to something which is greater than or equal to the objective value for any feasible vector. So if I can find appropriate y's, this expression, 2y1 plus 4y2, is an upper bound. So I get sigma, sorry. Okay. Let's try that again. I get an upper bound. Sigma star is at most 2y1 plus 4y2. If I get this, then I get an upper bound. Okay? All I have to do now is find appropriate values of y1 and y2 that satisfy all those constraints, and that gives me an upper bound on sigma star. But I don't just want to find any upper bound. I want to find the smallest possible upper bound. Okay? So I want to find values of y1 and y2 that satisfy all of these constraints, and at the same time minimize the value of this expression over here. So that means what I want to do is minimize 2y plus 4y2, y1 plus 4y2, subject to these constraints. And this thing in the red box is precisely the dual of this thing in the black box, by exactly the same rules that if you write it out as in terms of matrices. If I look at the matrix, the 3x2 matrix in here, or 2x3 matrix, as coefficients 1, 4, 0, 3, minus 1, 1, then there's a corresponding 3x2 matrix, 1, 4, 0, 3, minus 1, 1. Transpose the matrix. All of the upper bounds in constraints have turned into lower bound constraints. The 4, 1, 3 on the right-hand side of the red linear program, it's the same as the 4, 1, 3 in the objective value of the original linear program. The 2, 4 on the right-hand side of the original linear program becomes the 2, 4 in the objective value of the dual linear program. The max turns into a min. Right? So this is just syntactically how it's exactly the same linear programming problem that I would get by doing the syntactic transformation that seemed to fall out of the ether. But I can interpret it as I want to find magical values of y that have to satisfy certain linear constraints. And if I can do that, I get an upper bound on the objective, on the optimal value for that original linear programming problem. And on top of that, I want that upper bound to be as small as possible. And what the fundamental theorem of linear programming says is not only will I get an upper bound, but if I solve this LP, I get exactly the optimal solution for the original LP. Not just an upper bound, but an actual tight upper bound. Okay? Hopefully, this, there's been a lot of symbols here, and I recognize that this is not an easy thing to absorb in only one lecture. Hopefully the pictures that we'll see on Thursday will make at least some of this stuff a little bit clearer. All right, thank you.
Our lectures about extensions and max flow problems will be